what is 632.8 nanometers in meters? I think I'm just going to start with that question, and I'll wait for the second question until I've done this first one. So something that might help me out with this is to recall from the key concepts page that 1 meter was equal to 10 to the 9 nanometers. Okay. So I think there's maybe two ways of approaching this. Like one thing I could do, this is I think what I would like to call the substitution method for dealing with unit conversions, is I'm going to write down 632.8 nanometers as a quantity, and then I'm going to treat this nanometer unit kind of like it's a variable, just like you could do like in an algebra class perhaps. And I'm going to do a substitution. If I look at this equation up here, I think it implies that if I solve for nanometer, it would be equal to 1 meter divided by, if I divided both sides by 10 to the 9. So that's kind of like what I'm going to do as a substitution now. So that would let me write 632.8. And then again, for the nanometers, I'm just going to do that substitution of 1 meter divided by 10 to the 9. So again, this is the substitution method. It's a legitimate method. It's not as commonly taught these days. This is maybe a little bit old school in some ways, but sometimes it's useful for a quick thing to do this, and it's just one of the ways you can use one of these relationships. And in this case, I think that that will simplify to 632.8 times 10 to the 9 meters, which actually in scientific notation I probably want to rewrite that as 6.328 times 10 to the, oh, oops, that should be a minus 9 there, so make this a, right, because this was 1 over 10 to the 9, sorry about that mistake. So this should actually be 6.328 times 10 to the minus 7 meters. Now, another way I could have gotten to that result that is a little bit more like what you might have seen in another science class, let me write, 632.8 nanometers. I'll write again. This is what I like to call the conversion factor method, and I've heard it called either a unit analysis or dimensional analysis method in like chemistry classes. We're going to talk a little bit later about unit balancing in this class, and to me when somebody says unit analysis or dimensions analysis, that has a slightly different meaning to a physicist. So that's why I'm calling this like the conversion factor approach to doing unit conversions. And so instead of just doing a substitution, I'm going to multiply the 632.8 nanometers. Since I know that 1 meter is equal to 10 to the 9 nanometers, I'm going to multiply by 1 meter divided by 10 to the 9 nanometers. I know that this factor is equal to 1 because the numerator is equal to the denominator, and I also know that I can cancel, just like a variable again in like algebra, I could cancel the nanometers here, which means the only unit bearing symbol here, or a symbol that represents a unit that would survive, would be this meter, and I'd still have this division of 1 over 10 to the 9, that is, which would still do basically the same thing as it did here, and then simplify to 6.328 times 10 to the minus 7 meters. So let's turn to the second question. What about in inches? And I think for that one, what I'll do is I'll start out here. I'm just going to repeat this result one more time. 6.328 times 10 to the minus 7 meters. And this one I think lends itself, I kind of prefer the conversion factor method anyways, but it's good to be aware you can treat units like a substitution if you like. It's good to kind of like have that idea in your mind and recognize you can do that, because sometimes it's handy. But I'm going to now try to multiply by some appropriate conversion factors to get from meters that I've already got to inches. Now, okay, how do you deal with inches? Well, on the key concepts page, I'd written this relationship between an inch and a 2.54 centimeters. That's good, but I'm starting with meters here. So maybe what I could do here is I could multiply by a conversion factor. Like if I had a conversion factor of, say, 100 centimeters per meter, right? Because 100 centimeters is what's in a meter. Then these meters would cancel out, right? This is multiplying by 1. That's kind of the approach of the conversion factor method. And then you can always do more than one of these, right? So now I'm going to write another conversion factor based on the relationship between an inch and a centimeter. I'd like to have centimeters on the bottom, so I think I'm going to put the 2.54 centimeters down there, and then maybe I'll just put 1 inch up in the numerator of this conversion factor. And in my calculator, what I'm going to wind up doing here is like 6.328 times 10 to the minus 7. I'll want to enter that. I'll multiply, I make that a good multiplication symbol there, by 100 and divide by 2.54 0.54. So that's what I'm going to want to do in my calculator. But as these kind of cancellations of units show, the only unit that survives is inches. So let me go. I put that in my calculator earlier here, so I'm going to grab that and take a look at what it gave me for that. It looks, let's see, it gave like 2.491338, etc. Times 10 to the minus 5. Now this was given to me at 4 digits, so I think I'm just going to round off to that same number of digits. That is kind of following the significant digit rules that are common in science classes. I'm kind of hopeful that people have seen those before. I usually try to stick with them. I'm actually not like super picky about them on exams for the most part, especially on questions like this that are kind of, you know, well, this is just a conversion question, but maybe like I say book questions. Like in lab, we're going to be dealing with significant digits in a, whoops, I wrote the wrong number there, in a different way because we're going to be dealing with measurement errors and tracking those, and that's going to give us a whole different set of rules for dealing with rounding and how many figures, where do you round, those kinds of questions. It's going to be really, really different. But that's because you're doing a measurement and you've actually got an estimate of the error on your measurement. So we're going to do that in a slightly different and more rigorous fashion. So again, for this kind of stuff though, where there is no measurement error, I'm not super picky, but I try to at least demonstrate good, correct examples that most scientists would do. But again, I've usually not wanted to like mark off points if somebody didn't round off like exactly the way I would have. Let me check my answer here, and I think I didn't circle them, but it looks like we've got numbers that are matching up there with the units. I actually abbreviated the units to IN here, which is probably would have been proper for me to do, but I think everything there is looking good.